I think, yeah. And then we use our cell model for Friedreich Ataxia, the one with derived from the neuronal cells. And what you see is, again, I show here I think this is the cell growth. And as you see, the spectacular effect of the terrephone, which above 150 micromolar in controls completely block the proliferation of the cells. In fact, after that, it triggers death of the cell. And if you use mid-range concentration in the patient cells, you already have decreased growth at 50 micromolar concentration. So I think we should reconsider the use of these chelators because they might have at some step of the disease a very effective effect, because if you study the state where iron is the first rank in the disease, you will have a beneficial effect. On a long term, probably you might have, it can be predicted that you will have a problem. In particular, in Friedreich Ataxia cells, where aconitase is already low, if you completely trap the free iron in the mitochondria, then you will further decrease the aconitase. And that might be a real problem with this drug. Okay. I told you we had studied different parameters we know important in Friedreich Ataxia, so iron accumulation, and we discovered that there is a real problem to handle and manipulate iron in this disease. The second things we are really interested in is the oxidative stress and the mechanisms of oxidative stress. Several years ago, we've seen that the antioxidant defenses in Friedreich Ataxia were low. And we focused on one of these pathways, which is known as the NRF2 responsive pathway. NRF2 is what we call a transcription factor, something that controls the expression of genes. NRF2 is trapped, this factor is trapped in the cytosol on the actin filament. Actins are those filaments that shape the cells and that also plays a role in the antioxidant defenses. And upon an oxidative insult, NRF2 is released from the actin, and it goes to the nucleus, where it is able, with other cofactors, to trigger the expression of a number of enzymes involved in the detoxification of oxygen species and different kind of proteins. And we've got this spectacular data, because here you got in the control, what I told you before, the actin filament binding NRF2. Here is an antibody in green that show you where NRF2 is located. And as you can see in the control cells, NRF2 is tightly bound to the actin filaments. In blue, you have got the nucleus of the cell, two nuclei. Okay, so NRF2 is closely associated with actin in control cell. If you study the patient cell, NRF2 is completely disorganized, and you even do not mark the actin filaments. Show you that this NRF2 synthetic pathway is completely disorganized in the cell. Now, what happens if you stress the cell? I think here we use oligomycin. I'm not sure, I do not see that. I think it's oligomycin. If you stress the cell, in control cell, NRF2 that was on the actin filaments goes in the nucleus of the cell, and you see how the green light is in the nucleus. The same thing done on patient cells, show nothing at all, no NRF2 location in the nuclei, which shows that this system is completely flat in patient cell and does not react to oxidative insults. This is, in fact, due probably, we're still working on that, to the fact that actin is not organized normally in these cells, and because actin is not there, normally organized, NRF2 cannot bind to this to the actin filaments, and do not respond normally to oxidative insult. And we now have also some idea, but it's too preliminary to say, but the thing that probably link the absence of ataxin to the disorganization of actin is very important to identify, because it can give us a new tool to to solve this problem of oxidative stress sensitivity. Okay, I think that's only. Okay, so most of the work I've presented you were done by Vincent Pope and Sergio Gonzalez in our group, in Robert Wood Hospital. And okay, I thank you for attention.
Oui, alors, if there are questions, I want to ask you something. I have seen a paper that came out from a group in Rome, I think a few years ago, that was about glutathione of axia. Do you think that that may be one of the links?
Absolutely, working on that. So you have to know that one of the proteins that is involved in this glutathione do possess an iron sulfur cluster. And this iron sulfur cluster is a very, very particular compared to all the other iron sulfur clusters. It has another function. It's not a catalytic function. It has a function of a sink, a reservoir. And that makes the story come. Well, all what I say is a dream, so I don't know if it's true or not. But anyway, okay, it's only tell you that you might have, at a certain level of iron sulfur clusters, the iron sulfur cluster involved in catalysis are there working. But the reservoir of iron sulfur cluster is not there. So you do not respond to the oxidative stress. Because of the iron sulfur cluster are low, not absent, but low. But I know, we still have work to do. But we are in contact with those people in Sweden that have described all this other story. They didn't do the relationship between those two. But I hope we will have interesting things coming from that.
So it's very nice work. I have a question about the neuronal cell line. First of all, is this a stable cell line?
Yeah, they're stable. I mean, they're stable in the sense that they die rapidly.
No, but this is...
They are deficient. They grow for a while, then die. As predicted from the iron sulfur cluster deficiency. But you can start again from the initial soup, I would say, and you got a stable expression of that. They are very good model to test for drugs, I would say.
Okay, so they live a short time.
Yeah, in more than 1 week. See? So, but that's a very good model, I think, to test for drugs that ideal.
Yes. Now, then the second question is, obviously, have you tested idibinone or pigalitazone or on these neural models and see what happens?
Not really, because I must say the results you can obtain from idibinone completely, and like with all other cleanups, completely depends on the condition you use to test the drugs. In vitro, it doesn't really make sense to me to test these cleanup derivatives, because I know how to make them very toxic or very good for the cell. So I don't know. I mean, if you ask me to know if Nito-Q is better than idibinone, I can tell you whatever you want, because I know how to do it in cells. So I know that idibinone under some condition is a very important antioxidant, but I know the condition, so it's not very interesting. I don't know. For idibinone we didn't. I don't think we will. I don't think it's. I mean, it has to be tested in animal or in a more integrated system than the culture cell immediately.
All right. If